Hi students, this is Madhu Dharmapuri. Welcome back to the electrostatics lecture series. In this video, we are going to discuss about the most important nature of electric field, that is conservative nature of electric field. We have used this concept of conservative nature of electric field to derive potential energy difference formula as well as electric potential difference formula. Right? So what is conservative nature of electric field and how we can prove it? Right? So we know that every electric charge produces electric field in the space around it, and if we bring another charge into this electric field, that charge will experience some force because of this electric field. See, electric force is always due to the electric field. Electric force is always due to the electric field, and electric force direction is always along the electric field direction if it is acting on the positive charge. Right? If electric force is acting on the negative charge, then it will be opposite to the direction of electric field. Okay, remember these things. Right? So before we prove what is conservative, before we prove conservative nature of electric field, first we should know what is conservative nature. Right? So conservative nature means see, we can prove electric field as conservative in nature if work done in moving a test positive charge from one point to another point in electric field is path independent. If work done in moving a test positive charge from one point to another point in electric field is path independent. If we can prove this, then that is conservative. Electric field is conservative in nature. Or we can also say if total work done along a closed path, along a closed path in moving a test positive charge in electric field is zero. See, if you are moving a test positive charge in electric field in a closed path, means you are coming back to the same point, original point, after traveling some distance. You are coming to the same original point. The charge is coming to the same original point. That is closed path. If work done, total work done along a closed path in moving a test positive charge in electric field is zero, then also we say that electric field is conservative in nature. Right? From this point we can also prove that from this point line integral of electric field along a closed path is zero. This we can prove from this point. It means if line integral of electric field along a closed path is 0, then that electric field is conservative in nature. So if we can prove any one of these, that is the proof for conservative nature of electric field. The work done should be path independent, or the total work done should be 0, or you can say electric field, line integral of electric field along a closed path is 0. So this we can simply write from here, from this second definition. We'll see how it is. So because to prove the conservative nature of electric field, we need to find out work done. See here and here. First, let us try to calculate work done by moving a test positive charge in the electric field. Then see whether it is path independent or not. Or see whether total work done is 0 or not along a closed path. Right? So for that, what I am doing is, I am considering a charge plus Q at the center, at the origin of coordinate frame. You can see this here. Right? And this produces electric field in the region, in the space around it. Right? And its electric field at a particular point at a distance of r is this much, equal to 1 by 4 pi epsilon naught q by r square, and its direction is radially outwards because it is a positive charge. Due to positive charge, the electric field direction is away from it, so electric field direction is this way. Right? And let us take one test positive charge and move that test positive charge in the electric field produced by this charge. See, this is electric field produced by this plus Q, and in that electric field we are moving one plus Q naught, which is called as test positive charge, very small charge, and it is, let us say it is moving in this electric field by the external agency or by the help of external force, for example. Then we will calculate what is the work done in moving that charge, test charge in this electric field. See, if it is moving from A to B, the A is at a distance of RA from plus Q, B is at a distance of RB from plus Q, and I am taking some general point P, which is at a distance of R from plus Q. Here I have written vector forms, position vectors of this B, position vector of P, position vector of A. That is this OA RA, OA equal to RA, OB equal to RB, OP equal to R. This I will tell you a little later. So I have considered the position vectors of these positions with respect to origin or with respect to charge. Right? So what I have to do now? I have to calculate the work done and check whether it is path independent or not, or whether the work done is 0 along a closed path or not. I have to check it. Okay. So to calculate WAB means work done in moving from A to B, for example. Or I can say to calculate work done in moving a charge in electric field. Let a charge plus Q is located at origin O of coordinate frame which produces electric field, and in this electric field, consider a test positive charge plus Q naught is moving with the help of external force. See, what is the external force? That external force is exactly equal to the electrostatic force acting on that test positive charge. See, for example, if plus Q naught is at point P, for example, at point P, that plus Q naught will experience a force, F, electrostatic force, in this direction, which is equal to Q naught E, this way, right? And we are applying external force on this charge plus Q naught exactly opposite to this with the same magnitude, so that it neutralizes the electrostatic force and particle will not get accelerated during its movement along the path. So that external force is in this direction, opposite to it, and that value is exactly opposite to electrostatic force, which is equal to minus Q naught E. Because Fe is Q naught E and external force is minus Q naught E. So this external force is doing some work in moving this plus Q naught charge from one point to another point in the electric field produced by this charge. Okay, so this is the concept. So to calculate the work done from A to B, for example, to calculate work done from one point to another point, first let us divide the path into small, infinitesimally small parts of equal lengths. Then calculate work done in moving from one point to another point along that small path. Then adding all of them or integrating that will give you the work done from one point to another point, A to B, for example. Okay, so that we will calculate now. So these are the considerations to prove conservative nature of electric field or to find out work done moving a charge in electric field. Right? So these are the forces. Remember these values. Right? So let the path of the charged particle as a test charged particle is divided into infinitesimally small parts of equal length, say PQ equal to DL. So that is this. So this is the path, for example, A to B is the path that the test charged particle is moving. And along that path AB, I am taking a small path, which is very, very small path, PQ of length DL. Now, work done in moving a test positive charge Q naught from P to Q is how much? Is equal to, let me say dW equal to F external dot DL. F external dot DL. Work done in moving a test positive charge Q naught from P to Q. Because why I have taken DL? The displacement here is DL. PQ length is DL. So do not confuse with dr. So when we have calculated potential energy or potential, we have used F dot dr. But in those cases, dr, the charge is moving along the separation between two charges. But here the charge is moving along this AB, not along this radius vector or radial. Okay, dr is along OP and charge is moving along PQ or AB. So that is the difference. So we have to consider the displacement of the charged particle. Here the displacement is from P to Q. Okay, so this, right? So if this is the work done in moving a charge from P to Q along AB, then work done in moving charge Q naught from A to B is equal to WAB equal to integral A to B dW equal to integral A to B F external dot DL. F external dot DL. See, just integration of this. This is a work done along this small path, and this is work done along this AB from A to B. So this direction. Okay. So now what I am doing, WAB is equal to F external, we know that minus Q naught B, so I am substituting that. A to B E dot DL. F external is minus Q naught B bar, minus Q naught is constant, so this. Okay, so let us take this as equation number 1. Equation number 1. Okay, FWAB equal to minus Q naught A to B E dot DL. Okay, this is clear? How we have written? Just simply from force into displacement formula. And we know force is this much. Right? Right. So WAB is equal to minus Q naught A to B E dl cos theta. A to B E dl cos theta. And now look at this picture. This picture is the enlarged picture of this region. See, if this is n, for example, and with this length is dr, this length is dr, pn is dr, and pq, it is dl, and the angle between E and dl is theta. Here theta is angle between E and dl, remember. Okay, so this is E, this direction is E, and dl is this way. So this picture is enlarged picture of this, and this pn, I am taking it as a small length dr. Okay, so from this picture I can write cos theta is equal to, see, this is 90 degrees. This is the normal. Qn is normal. Okay, Qn is normal. Okay, so this is 90 degrees. So this will be hypotenuse. So this is adjacent side. So cos theta equal to dr by dl, and dr equal to dl cos theta. Dr equal to dl cos theta from here. And this can be replaced with that minus q naught a to b e dr. Simply dl cos theta is dr. Okay, and we know from this WAB is equal to minus q naught E is this one. So 1 by 4 pi epsilon naught q by r square dr, and it is from A to B. So we are substituting electric field, which depends on the distance of that point from charge q. So A to B means A is at RA and B is at RB from charge. So this integration will be, so minus, it's a q naught by 4 pi epsilon naught is constant, RA to RB minus 1 by r square dr. This minus is inside. So q naught by 4 pi epsilon naught minus 1 by r square is 1 by r, integration RA to RB, and then WAB is equal to q naught by 4 pi epsilon naught 1 by RB minus 1 by RA. So let us take this as equation number 2. So equation number 1 was WAB in terms of electric field, minus q naught A to B E dot dl, and here we in terms of, you can see, RB and RA. Right? So if you observe this picture, if you observe this formula, it is very clear that it is work done is depending on only RB and RA. Work done is depending on only RB and RA. What is RB? This one. What is RA? This one. Means RB is depending on position of B, RA is depending on position of A, which means work done is depending on the positions of A and B. Right? Work done is depending on the positions of A and B. No matter which path is followed. For example, see, this is AB. So you can follow this path. AB is fixed. You can follow this path. AB is fixed. You can follow another path. AB is fixed. See, RA is not changing. RB is not changing for all these paths. Work done depends on only RA and RB. No matter which path you have followed. That means we can say that work done in moving a charge from one point to another point is path independent. From this it is very clear. From this it is very, very clear. Right? So we can say first shall we see WBA also, so that then we can write this conclusion. For example, if I want WBA, means B to A, if a particle is moving from B to A, so if I take this path, for example, B to A, right? So B to A, what is the work done? I can write it as minus Q naught. It is actually F external dot DL B to A. So WBA is equal to minus Q naught B to A E dot DL. So let us give this as equation number 3, and WBA is equal to minus Q naught. E value is this much. Sorry, here first let us write this one, EDL cos theta B to A, and WBA, same steps. Okay, that's why I'm just writing it. B to A, EDL cos theta is dr, so it is EDR, and WBA equal to minus Q naught R B to RA. E is what? 1 by 4 pi epsilon naught Q by R square dr. Right? So what is the next step? Integration of this. So WBA equal to Q naught by 4 pi epsilon naught RB to RA minus 1 by R square dr. Right? So moving this. So this is equal to Q naught by 4 pi epsilon naught 1 by R RB to RA, which is equal to WBA equal to Q naught by 4 pi epsilon naught 1 by RA minus 1 by RB. Let us give this as equation number 4. Equation number 4. See, you can also see this. Work done in moving a charge from B to A is again depending on the positions of B and A. It is depending on only RA and RB. It is depending on where the positions are, not the path. The work done is again path independent. You can check this here. This also you can follow. You can follow another path. So this is how you can move. But ABs are not fixed. AB positions are fixed for all these paths. If AB positions are fixed, RA and RBs are not changing, then work done is not changing. Means work done is constant for all paths. Right? So from this, what we can conclude from equation 2 and 4? From equation 2 and 4, we can write that. So is this clear? So I'm removing this. Right? Okay. So let me write it here, for example. From equations 2 and 4, it is clear that work done in moving a test charge depends on initial and final points. Initial and final points, or you can say RA and RB. RA and RB. They are depending on only A and B. Right? moving a test charge depends on initial and final points. That is, work done is path independent. We can write this. It depends on only what is RA, what is RB. Not which path we have followed. Not which path we have followed. We can follow any path, but if it is coming from A to B, it depends on only RA and RB, the distance of A and distance of B from the charge. So work done is path independent. So this is the proof for conservative nature of electric field. The first definition that we have seen in the beginning of this lecture. Right? So this is clear from 2 and 4. Right? And one more thing also we can write from this 2 and 4. Right? What is equation 2? The equation 2 was, this was equation 2 actually. WAB is equation 2. Q naught by 4 pi epsilon naught 1 by RB minus 1 by RA is the equation 2. You can check it. Okay. So from 2 and 4 again, right? Add both of them. So WAB plus WBA is how much? Q naught by 4 pi epsilon naught 1 by RB minus 1 by RA plus Q naught by 4 pi epsilon naught 1 by RA minus 1 by RB. So this plus this. It is very clear from this is Q naught by 4 pi epsilon naught is common. 1 by RB minus 1 by RA plus 1 by RA minus 1 by RB. It is cancelling each other. It will be 0. So WAB plus WBA is 0. Which means total work done in moving, let's say, along a closed path, in moving a test positive charge is 0. Again, it is conservative in nature. The total work done along a closed path in moving a test charge is 0. What does that mean? For example, you are here. For example, you started from here. The charge Q naught is started from here. So work done in moving a particle from A to B along this path is this one, equation 2. And now we are going back. The charge Q naught is going back from B to A along this path. The work done in moving plus Q naught from B to A is this one. So this plus this is the work done in moving a charge along a closed path. So starting from here, reached B and coming back to A. So this is closed path in green color. So that work done is 0. Conservative in nature. Very clear. Okay. And from this, as I said, we can infer another important point. That is it fine? Okay. So now I am removing all this. From equations 1 and 3. What is equation 1? WAB is equal to minus Q naught A to B E bar dot dl. This was equation 1. Okay, and WBA minus Q naught B to A E dot dl was equation 3. Right? So from equation 1 and 3, add both of them. WAB plus WBA is equal to minus Q naught A to B E bar dot dl plus, so this is minus Q naught B to A E bar dot dl. Right? So from here minus Q naught is common. So A to B E bar dot dl plus B to A E bar dot dl, which is nothing but minus Q naught closed path A to B and B to A. So E bar dot dl along a closed path. This is equal to this, and this is WAB plus WBA. And we know that, let us say this is some equation number 5. Equation number 5. From equation 5, this is 0. That means minus Q naught E bar dot dl is equal to 0, which means E bar dot dl is equal to 0. So this is another one you can see. This we have got from here. The total line integral of electric field along a closed path is 0. Conservative nature of electric field. Total line integral of electric field along a closed path is 0. So conservative nature of electric field. So we have proved all these things. Work done by the external force moving a charge from one point to another point is path independent. Work done in moving a test charge from along a closed path is 0. And the line integral of electric field along a closed path is 0. Which are the definitions for conservative nature of electric field. So now we can say that electric field is conservative in nature. Right? So that is what the proof. So you can say this is some equation number 6. You can write here that from equation you can say 2, 4, 5, 6, we can confirm that electric field is conservative in nature. Electric field is conservative in nature. Right? And from equation 6, let me extend it. From equation 6, that is integral E dot dl is equal to 0. Right? And from Stokes' law, integral E dot dl is equal to del cross E dot ds from Stokes' law. So we say that integral del cross E dot ds is equal to 0 and del cross E is equal to 0, which is very, very important concept here. Curl of E is equal to 0 here. That is curl of E, which means that we can say electric field is irrotational. If curl of some vector is 0, that vector we call it as irrotational. So here electric field is irrotational because del cross E is equal to 0. Right? So this is one of the important derivation that we can get from conservative nature of electric field. Right? Electric field is irrotational. Right? So if electric field is irrotational, we can confirm from this concept that from here I can write that since E is irrotational, electric field lines do not form closed loops. They do start from positive charge and end on negative charge. Which we have already discussed when we have discussed electric field lines. So electric field cannot be rotated, or we can say irrotational. So they do not form closed loops, and they do start from positive charge and end on negative charge. This is one of the consequence from this, right? And the second consequence we can write as since curl E is equal to 0, from vector calculus, curl of gradient of scalar is 0. Hence E can be written as E equal to minus del V. This is another important consequence we can write, which we have already discussed in one of the previous video lectures, relation between electric field and electric potential, the negative gradient of scalar. If curl E is 0, then E can be written as this, because curl of gradient of any scalar is 0. Here scalar is electric potential. Okay, so hope you have understood. If you have any doubts regarding this lecture, you can put your doubts under the comment section. Thank you very much.